Section 2. Now we're going to be calculating volumes. Not just areas. Volumes. No. A solid of revolution is going to be the first 2/3 of this section. Solids of revolution are the result of a region in a plane. Regions in a plane are what we have been working on in the first section, finding the area of the region. But now we're going to take that area and revolve it about a line. The line in this case is called the axis of revolution. We will revolve it completely around the line, which will create a volume. And this is a process that is used in all over the place in our lives. All of these examples right here can be modeled as solids of revolution, where they have a cross-sectional area and then we revolve that area about some line. So axles, your pills, holes, funnels, eggs, bowls, bottles, cans, satellite dishes, pistons, jet engines, contact lenses, anything that has some sort of circular property to it can be modeled using this math right here. And they are modeled using that math. All of these things have something in common. They have a circular cross-section. If I were to cut like this can right down the axis, so I got some sort of cylinder-looking thing here, maybe it's a pop can, I don't know. But I cut it right here and I take a look at it, the cross-section looks just like that. It's a circle. And the same thing is going to be true of any of these things if I cut them down the axis, or down the, not across the axis of revolution. I'll see a cross-section that's a circle. Okay? If you think back to geometry, what is the volume of a right circular cylinder? Well, I have a right circular cylinder sitting right here. How do you calculate that volume? If you need to make a trip to the pencil sharpener, I guess you're looking for the volume of a right circular cylinder. Oh yeah, we all remembered it all of a sudden. It's pi r squared times the height. It's not on the pencil sharpener, but it is on this page at the bottom. Okay, so we have a right circular cylinder. In order to find the volume of the cylinder, what you actually did was find that first. What is that? It's the area of the circle. And then you multiplied by, in this case, that would be the width. Right? But if I had a right circular cylinder that was upright, then you'd be multiplying by the height. So it's just the area of the circle times the height. Oh, you said that? Oh, well, say it louder. I would have rehired you. So, come back to me. The volume of a right circular cylinder in geometry is V equals pi r squared h. Okay? Now, if I were to just take a slight section of this right circular cylinder right here, I'm going to call it a disk. What would the volume of that disk be? The area of the circle, but that disk has some thickness to it. Times the height of the circle. Yeah. So this disk that I'm cutting out of here has a thickness to it, right? Whatever that thickness is, I don't know. I can make that disk that I cut out as thick or as thin as I want it, right? Which means I can call it what? Delta X or delta Y, depending on the orientation of the disk that I'm cutting out. In this case, this would be delta x. In this case, this would be delta y. Okay? So obviously, the thinner and thinner I get on this disk, and then I start adding up all of these disks, eventually I'll get the volume of that cylinder. But the thinner and thinner I make that disk, the more accurate I will get for a volume, until eventually that disk becomes infinitely thin, and then I get a completely accurate answer for the volume of that cylinder. For a cylinder. The reason that I'm saying this is because we're not going to be working with cylinders. We're going to be working with screwy shapes that will be revolving about some line. And they won't have nice, neat formulas like this. Pi r squared W is the same as pi r squared H, which is basically saying the area of this little disk times the width of the disk. And if I add up all of those little disks, I wind up with the total volume of this figure that I'm generating. The disk method is the first method that we're learning in this section. There is another one that we're going to learn, and then there's a third one that we're going to learn, all in this section. And then the last section that we're going to do is a fourth method. So the disk method forms disks of width delta x or delta y. But for now, we'll start with delta x, across the duration of the area being revolved. And then you're going to accumulate a bunch of disks together to form the entire shape that you're looking at. Now, what I'm going to recommend that you do, like with the little party favor that I just showed you, is you try to visualize this thing that you are creating. Try to form a mental picture of what this shape actually is going to wind up looking like. I'll tell you that this right here, when you revolve it about this line, is going to form one of two things in your mind. For me, when I revolve this about a line, it forms basically the exit nozzle of a jet engine.
Oh, yeah.
Can you see it?
No.
That's what I see. We are revolving about this line right here, okay? So this shape, this little shape, will revolve out of the page and then back within the page and come back out. And it's going to form this sort of nozzle-looking shape, okay? If you've ever watched pictures of the space shuttle, you will see the solid rocket boosters have this sort of shape to them, and so do the engines on the space shuttle, that they can adjust to moderate the flow that's coming out and give whatever it is, either the rocket booster or the space shuttle, more or less thrust. Because basically that's the only way you can control a rocket. All right? Now, you could also think of this as a sideways Hershey kiss with the top cut off. Do you see that one?
Yeah.
All right. It is incredibly important. It's critical that you try to visualize what this shape looks like before you try to revolve it, because then that will help you set up your representative rectangles and also your integrals. If I take that Hershey kiss and I cut it this way, am I going to get a circular cross section? No. I have to cut it this way, right?
So
Opposite of the axis of revolution, yeah. Perpendicular to the axis of revolution, okay? So in this problem, we are going to revolve about this line right here. So what I'm going to do is I'm going to draw a little arrow showing that I'm revolving about that line. Now, the accumulation of disks combined with making delta x smaller and smaller yields the exact volume of the entire solid once we generate it. So we need to draw in a representative rectangle.
So we're assuming that this is like we're making this.
We are going to make a solid figure, yes, an entire
And find the area of it.
three-dimensional object. We need to find the volume of it, okay? So this object is going to be the sideways Hershey kiss with the top chopped off, or a jet engine, okay? So, in order to do this, we need to create a representative rectangle. Now, that representative rectangle, when I revolve this thing about this axis of revolution right here, will turn into what? A disk. Think of like a quarter, okay? This thing right here is going to revolve out of the page and back into the page and back around, and it's going to create a very thin but round disc. Okay? Now as I slide, because this is a slider, as I slide that round disc from the left to the right, and I make that disc thinner and thinner, as I slide it from the left to the right, eventually I will accumulate all of the area that you see here, but if I have revolved this thing around, I'll be accumulating volume, not area. And I will eventually, with that disc, accumulate all of the volume of this entire shape. You have to be able to visualize that.
The amount of concepts has changed.
Yes. When it clicks, you will see it and you will be just fine. Okay? For right now, we have to set up this representative rectangle here, because this thing is going to revolve around and get me a representative disc that I have to accumulate.
Okay.
So now,
The point of the rectangle.
We're all so excited.
and now, once you create your representative rectangle, the height of this rectangle is going to be called capital R of X. Because capital R of X, this height right here, acts like the radius of that disc. Okay? So this distance right here is capital R of X, and we're using capital R because it is a radius as you revolve that thing around. The width of that representative rectangle is delta X in this case because of the fact that this is the x-axis, well, this is the x direction right here, and we would be going from one x coordinate to the other, so that has to be a delta X. If that was a horizontal representative rectangle, which, and we'll get there, then that would be a delta Y. Okay.
I'm following for the first time.
Good. So now the area of a rectangle, of course, is the height times the width, right? So the height is R of X times the width, which is delta X. So then the volume of the representative disk that we will create by rotating this thing around, this axis of revolution right here, is found by doing volume equals pi r squared h, right? Yeah. Okay. Well, then the change in volume that we get as we accumulate volume from this representative disk is equal to pi times the radius squared times delta x. Now, if we integrate it using calculus, then the actual volume of that shape is going to be pi times the integral from a to b. This would be a right here. This will be b. As I slide this slider across, I accumulate that area, which means I accumulate that volume of the radius, which is the height of that rectangle being squared, times the width of that representative rectangle, which as I let that representative rectangle go to infinitely small, it becomes dx. Now I integrate it, and I wind up with the volume of this jet engine, or this Hershey Kiss with the top cut off. So I have a setup for both of these situations. We have a horizontal axis of revolution or a vertical axis of revolution. The horizontal axis of revolution is going to be that guy right there. The vertical axis of revolution is going to be that guy right there. So it doesn't have to be the x-axis or the y-axis. It can just be a horizontal line or a vertical line. That's why I'm not showing you axes here. But the axis of revolution will be the edge of the cross-section. So that as this thing gets revolved around, it would create an entire object, like one of those candies with the goofy white sprinkles on it that's usually like pink or blue or yellow that you see around Easter time. That's what this one would be, right? Do you see it? Yeah, they're very flat. This one, if I revolve this way, this would look more like a gumdrop. Do you see it? Try to see those shapes before you even start the problem. You do get to use your imagination. All right, so I have a horizontal axis of revolution here. Horizontal axis of revolution, which means that my representative rectangle needs to be oriented which way? Vertically. Here's my representative rectangle, which means that my radius, r of x, will be this. And I have a delta x for the width of that rectangle. And my slider that I have set up, my representative rectangle, will slide from A to B. Okay? With a vertical axis of revolution, this time my representative rectangle needs to be what? Horizontal. Because if you look at the bottom here, this paragraph, the representative rectangle will always be perpendicular to the axis of revolution for the disk method. In this case, my radius then, r of x, is not r of x anymore. It's a function defined in terms of y. And my delta x is not delta x anymore. It's delta y. So you have to keep that in mind. With the disk method, that horizontal representative rectangle, if you draw that rectangle in there, it will remind you that you have to be delta y, and therefore your function has to be in terms of y before you set up your integral. Also, the variable of integration will always be the same as the variable used to describe the width of the representative rectangle. So that's how you set up these problems conceptually. If you can do this, then you can do the problems for sure. So next time we'll get into the practice problems that we have for the disk method, and then once we're done with that, we'll also move on to the next method after the disk method, which is called the washer method. It's very exciting.